are now going to look at theme 2, which is gas mixtures. In theme 1 we looked at gases as pure. Now we're going to look at them as gas mixtures, and we're going to start with ideal gas mixtures. So for ideal gas mixtures, whenever we start looking at ideal gases, what we're supposed to remember is, okay, whether ideal or non-ideal, that these gases have got properties. So these properties include the enthalpy, the entropy, the Cp, the molar mass, specific enthalpy, and specific entropy. So in order for us to, for ideal gases or real gases, it is easy to find if it is not a gas mixture, if it's just a pure gas. So we have to find a way in which to make things easier to find if it is a gas mixture. So we're going to learn some new terms. The first one will be the mass fraction. So mass fraction. So the mass fraction is denoted by Ci, and the formula for the mass fraction is Ci is equal to Mi over the total mass. So this is epsilon Mi, which is the summation of Mi. This is the summation of Mi, which is the total of the masses that are in the mixture, and this is the mass of just one gas which is in that mixture. So yeah, so Ci is the fraction of the mass of a gas in a gas mixture. So this can also be in cases of mass flow rate. So each gas might have a different mass flow rate. Please observe here that this is a mass flow rate, this is a mass flow rate, and this is just a mass. So for mass flow rate, you can also do the same, which is just a fraction. If you see this is the mass of just one gas, and then this is the mass of the total mass of the mixture. So Mi over Mi, which is over the total Mi, which is the fraction, which is also the mass fraction. Then the second thing we're going to learn is the mole fraction. The mole fraction is denoted by Yi. So Yi will be equal to Ni over N total, which is equal to Ni over summation of Ni. So this Ni is the mole of the gas involved in a volume, and then this is a total number of moles, where you just add each mole in the mixture. So this can also be expressed as Yi is equal to, in terms of the flow rate, which is the mole flow rate. Then if we play around with these equations, we can have Ci is equal to Yi Mi over Yi Mi. This Mi is the molar mass. Then the same one, we can have Yi is equal to Ci over Mi over the summation of Ci over Mi. Please remember that this Mi in here is the molar mass. And always remember that Ni, which is the mole, is equal to the mass over the molar mass. The second part we're supposed to look at is the non-ideal gas mixtures. Please be aware that in MTX 311 we do not look at non-ideal gas mixtures. This is because this is too complex for us to solve, and so we do not look at it. The only gas mixture that we might look at, which is non-ideal, is a mixture of air and steam. Okay, so after that we skip this. So please note, whenever you find where you have to find properties, you find such a question with gas mixtures, please do not even try to see if it's ideal or non-ideal. Just go ahead with the ideal. I'll just cancel it so that you can remember that we do not look at non-ideal gas mixtures. So now I'm going to introduce you to another thing, something else. So the thing I'm going to introduce you to is partial pressure. So partial pressure is written as Pi. So partial pressure, when a gas mixture is in a volume, each gas has got its own pressure. They do not have the same pressure. So please note that every gas in a given volume has got its own pressure, but the temperature is the same. The temperature in a gas, the temperature in a volume, in a given volume is the same for every gas. The total pressure in a given volume is equal to the summation of the partial pressures. So I'm going to need you to remember this equation. PV is equal to mRT, which is for ideal gases. So what we're going to do now in gas mixtures is, we said each gas has its own pressure. The volume is the same since it's in the same container. And then it also has its own mass and its own R value, but the temperature is the same. So if we want to find the partial pressure, if we want to find the partial pressure, we can just make it the subject of the formula over V. Remember, V and T remain constant for all gases, for the whole gas mixture. Then Mi and Ri change because it's for the partial gas. So we're just going to do an example. So for this example, let's say we have gas in a volume of 1 cubic meter. The temperature is equal to 300 Kelvin. Then these gases we have we're going to have 10 grams of hydrogen, 200 grams of water, which is obviously steam since we say it's a gas, and then we have 500 grams of nitrogen. So let's say we want to find the partial pressure of each gas. If we want to find the partial pressure of each gas, what we do is we make a table using the same equation, which is PV is equal to MRT. So what we're going to do is we're going to make a table here. So this table, in here we're going to put the gases. So we're going to start with hydrogen, then we're going to have water. Okay, let me just note that this is an example. Then the next one will be nitrogen. So in the next column, we're going to have mass in kgs, and then we're going to have R in kilojoules per kg Kelvin. Okay, this is just a rough table, so don't worry about it. Then we're going to have the temperature in Kelvin, and finally we're going to have the pressure in kilopascal. So we know that the mass here is 0.1 kg, sorry, 0.01 kg. Then we have another mass of 0.2. Then we have N2, which has a mass of 0.5. Then these are the R values. 1, 2, 4, 3, 0.4615, of which you can obtain in your thermodynamic handout. Then 0.2968. Remember, the temperature is 300, 300, 300 for all of them. So what we now do is we use this formula here. This is the formula we're going to use. So for H2, if we get this 0.01, which is the mass, we put it there. Then we get Ri, we put it there. Then the temperature, we put it there. Then the volume, we use the same one, 1 cubic meter. What we're going to have is 12.37 kilopascal. Then for water, what we're going to have is 4.47 kilopascal. Okay, so let's just calculate now for N2 so that you can see how this goes. So for N2, what's going to happen is we're going to say Pi is equal to 0.5 times 0.2968, then times the 300. Sorry if you can't see. Okay, 300, then over the V, which is 1. So the Pi will be equal to, let me just get a calculator, 0.5 times 0.2968 times 300, which is equal to 44.52, which will be our pressure, kilopascal. Okay, so if you tried it out, try out this one here. Okay, I just want you to see something. Pi is equal to, we get the Mi for water, which is 0.2 times the Ri for water, 0.4615 times 300 over 1. This will be equal to Ti. Let's just get the calculator. It will be 0.2 times 0.4615, then times 300 Kelvin, which will be equal to 27.69. So if we just use this method, what we're going to find out is that it will be, this here will be 27.69. So The difference in these two pressures comes about because at the given temperature, the saturation pressure for water is 4.47 kilopascal. So if the pressure that you find at that point of the gas is greater than the saturation pressure, you take the saturation pressure as the pressure of the gas. So which means that the mass of the gas which has condensed has decreased.